Welcome back to ROBT402 Robotic Mechatronics System Design course, Lecture 10, Programming Timers in TIA. We have some slides also on programming timers in codices, and you could learn programming timers in codices as well. Today's topics are as follows: PLC timers, programming example, and programming exercise. Timer instructions. PLC timer instructions that provide the same function as timing relays. There are two main PLC timer instructions: semantic timer functions and IEC timer functions. So as we discussed in the introduction to the TIA lecture, you have noticed that for any instruction we could have legacy semantic one and IEC ones. The IEC ones are very similar to one that you could find also in codices, because codices is based on the IEC standard, and semantic are specific to TIA and they only work with the Siemens PLCs. So here you could go to the basic instructions in the TIA and you could find timer operations. Under timer operations, the first one listed are IEC, and under the legacy, you could find the semantic timers. What type of timers we have? We have pulse generation, extended pulse on delay, retentive on delay, and off delay timers. Pulse generation, the output signal is at least as long as the start signal, but its maximum length is equal to the set duration. Okay, so it might be a bit confusing from the description. I will go through the description, but later in the coming slides, I believe maybe the next slide, we have a nice graph that you could learn and understand these timers better. Extended pulse, independent of the duration of the start signal, the output signal is as long as the set duration. On delay, if the start signal is longer than the set duration, the output signal begins after the set duration and lasts until the end of the start signal. Retentive on delay, independent of the duration of the start signal, the output signal begins after the set duration and ends when the timer function is reset. Off delay, the output signal begins with the start signal and ends after the set duration has elapsed after the end of the start signal. Again, you might need to back to this slide and read those descriptions again. A data record which is present in the system data is permanently assigned to each semantic timer function. This limits the number of semantic timer functions. So based on the hardware PLC that you have, you may have some limitation on the number of timers or counters, because they have different capacity and size of memory. Semantic timer functions are global tags. The symbols are declared in the PLC tag table. So same as any other instructions and variables like a Boolean contacts and coils, it will be listed in the tag table. The semantic timer functions run in the startup and run modes. Okay. Semantic timer functions as overall function represented as a box. So you see in the ladder programming or in the function block diagram programming or in a structure control language, they have a different format, or a structure test language, they have a different format Okay, and um, basically they have also some variables, but variables are almost the same between them. For example, S and R and Q and um, BCD and BI, they are almost the same between different type of languages. You are so far mostly familiar with the ladder programming language, but as we go forward, you might use other type of languages as well. Okay, so this is a nice graph that I said in the previous slide that describe different types of timers better than those descriptions. The first signal is the start signal. So in the ladder programming, for example, you see that the first signal is the start signal. This is the signal that triggers the timer. So once it goes true from false, then the timer is active. Now, depends on the type of the timer, we expect different outputs. For example, for the pulse timer, it is true for the duration of the pulse. And that duration is, for example, here is T. After that, the output of the timer, which is the Q or the downbeat, will be false. The extended pulse, you see that even after the start signal goes off, it will be extended or could be extended after that time. That's why they call it extended pulse. On delay timer, from the name is clear that this is a delay timer and it is on delay. It means that the start signal should go from off to on. So when it goes from off to on here, then after a delay of t second, the downbeat of the timer becomes true, but the downbeat will go again off when the start signal goes off. We have a retentive on delay timer, and retentive on delay timers basically keep the time, and you see that they don't go off after the start signal goes off, so it will stay on until we reset it. So see that there is also one reset signal here, and this is a time value. The second one is time value, the or defined duration or time value, and the R is the reset input. So for the retentive timer, we have to reset it, otherwise the downbeat doesn't go to 0. And the off delay timer, as it is clear from the name, the start signal should go from on to off. And once that happens, the downbeat doesn't go from on to off immediately, but it will go to off after a delay of t second. All of these definitions are the same for the codices. You could find on delay, off delay, and retentive on delay timer also in codices. Semantic timer functions as single element also. These are mostly the legacy one, the semantic one, not the IEC one, and I don't spend much time, but anyway, you could discover them by yourself. Read the description and see how you could use them. There are similarity between the semantic one and IEC one, but they are slightly different in terms of the application and instruction. So I'm gonna leave that to you if you wish to install it. For the purpose of this course, I strongly recommend students to go with the IEC instructions. TP, T on, T off, and T on are pulse generation on delay, off delay, and accumulating on delay timers. An IEC timer function is a statement with its own data. When programming a timer function, you specify the data block in which the data is to be saved. If you select a single instance bottom, it must be different data block each time. If you program a timer function in a function block, you can also select multi-instance. In this case, the data of the timer function is saved as a local instance in the instance data block of the function block. The duration of an IEC timer function can have the data type time or L time. Accordingly, the data structure of an IEC timer function is mapped in the system data type SDT IEC timer or IEC L timer. So if I want to put that in a simple word, every time that you create a timer in the data block, you will have one instance of the timer, because that timer has it needs memory, it has a preset time and other information that should be saved inside the memory. Quantities associated with timer instruction. Preset time, or PT, represent the time duration for the timing circuit, and elapsed time, ET, represent the amount of time that has elapsed from the moment the timing started. Undelayed timer instruction. An undelayed timer is used when you want a time delay to occur before an instruction becomes true. So here we have input and here we have the timer, and the run condition goes from false to true. So here the input becomes true from false. Now this is the time period. The time period starts right after the input goes to true. So this is similar to the start signal. However, the time output bit, or the done bit, or the Q bit, goes to true from false, or goes on after delay of preset time value, or the specific time that we have given to the timer. So similar to the codices, no differences between TIA and codices in terms of definition of undelayed timer. So in the codices, you could refer to these videos to learn more about undelayed timer and using TON, or undelayed timer, and up counters block in a structured test programming codices, so either in ladder logic or a structured text. Also, you could watch related videos to industrial automation course on my channel and learn more about codices. PLC undelayed timer program. So here we have one example of undelayed timer. We have an input. This is an undelayed timer. You see that we have a preset time value of 10 seconds. The time base here is 1 second. This is a basically time interval, which is a standard for the codices and TIA both. This is accumulated time when the timer is started, and this is a down bit of the timer or the Q in the TIA portal. Enable is true when the timer becomes enable or the start signal becomes true. Okay, so Here we have one switch, input A, and we have three pilot light, green, red, and yellow. We call them output B, C, and D. And we have used enable bit of the timer in this contact format to turn on and off the output B, which is a coil, which is our output. Okay, so as soon as the switch goes on, then the output B will go on. We have TT. TT is basically will become true once the timer is enabled but not yet done. And in some programming languages you have access to this specific variable, and in some you don't. For example, in Codesys you don't, so you need to program it. So if you watch related videos on how to use on-delay timers in Codesys, you will learn how to program this specific line. And at the end we have a down bit, so once the timer is done after 10 seconds, the output D, or the yellow pilot light, will go on. You could see how this program is implemented in Codesys in the following video. I strongly recommend you to watch these videos if you haven't passed industrial automation course with me, so you could learn about programming timers in Codesys, and also in general you will learn about programming timers and the concept of timers. PLC sequential motor control program is another example. In this example we have 1 and 2 push buttons and 1 pressure switch, which is basically a pressure sensor. And for outputs we have motor 1, motor 2, and motor 3, and these are overloads. These are overloads. So if these motors are overloaded, then they will be shut down by this contact. Okay, so the first push button is normally closed and the second one is normally open. So you see that we have a green, so it means that this one is true because it's normally closed. So we need to press push button 2 to start the motor. So push button 1 could be stop switch for the emergency cases. So we need to press that to stop it. That's why you have it normally closed 1. So anyway, when we press push button 2, the motor M1 will start, and you see that we have this latch contact here. That latch contact will keep the motor 1 running even though this push button 2 is released. Once the pressure sensor or the pressure, let's say, could be anything, could be pressure of the oil, for example, reaches to a specific level, this pressure sensor will go on and the motor 2 will be on. And we have a timer here with the preset time value of 15 seconds. This is an on-delay timer, will start or will go on. The down bit or the Q bit of the timer will be true after 15 seconds, and the motor 3 will be energized after 15 seconds of this pressure sensor going on. This is just one example, and for the sake of this example, I don't care much about why this program is written or what are the function of these motors exactly. You want to learn about timers. Off delay timer instruction. The off delay timer operation will keep the output energized for a time period after the line containing timer has gone false. Very similar, we have this input enable bit or the signal bit that should go from true to false, because this is an off delay timer, so the timer will be activated once this signal bit goes off. Here for the TIA portal programming environment, you see for the IEC timer, for the off delay type, in is basically the signal, and PT is the preset time value. In this case, for example, is set to 15 seconds, and after 15 seconds the down bit of the timer will go off. So this is the difference between the on delay and off delay. For the on delay, the down bit will go on, but for the off delay, the down bit will go off. Will go off or false with the delay of 15 seconds from the signal bit. Here we have one example of off delay timer. We have one switch. We have an off delay timer with delay of 15 seconds, and we have a down bit here and a pilot light. So once this switch goes from on to off with a delay of 15 seconds, the pilot light will go off. For the codices implementation, watch this video to learn more about codices. Program for switching motors off after 5 seconds of interval. Here we have one switch and we have 3 motors, M1, M2 and M3. Once this switch is off, so when we turn it from on to off, the first motor will go off after 5 seconds. Why? Because we have used the down bit of the first timer to turn off the first motor. The second motor will go off after 10 seconds because we are using down bit of the second timer to control the second motor, and after 15 seconds the third motor will go off. Another example here for fluid pumping process. We have tank A, we have tank B, and we have a pump to pump fluid from tank A to tank B. Before starting, PS1 must be closed. PS1 is pressure sensor 1. So we need to have certain level of pressure to operate the pump, let's say. When the start button is pushed, the pump starts. If the PS1 is true, PS2 and PS3 must be closed 5 seconds after the pump starts. Okay, so these two must be closed after 5 seconds. If either PS2 or PS3 opens, the pump will shut off and will not be able to start again for another 15 seconds. So we need to have this automation in place, and we want to see how we could program it. Okay, here is one solution. Please be aware that we don't have, many times we don't have unique solution, and you could come up with different solutions. However, we have one solution here presented for example, and you could learn. We have stop button, which is normally closed, start button, normally open. We have pressure sensors PS1, PS2, and PS3. We have used here two timers, one with a preset time value of 5 seconds and the other one 15 seconds, as it is requested in the description of the problem. And here, once the start button is pushed and the down bit of the second timer is not yet done. Why we have used that? Because we wanted that 14 seconds of let's say silence or safety. We couldn't be able to turn on this pump after that 14 seconds. So normally that down bit is false, so we have used the negated contact here, so this one should be normally true. And also this pressure sensor 1 is true, then the pump could go on. Also we have this pump contact latch here, just because if this start button is released, we want this pump keep running. Okay, so once we have this pump running, now we want the second timer to start timing. Okay, after 5 seconds of this pump running, the down bit of the timer will become true. Now we have this down bit here is true, and we could proceed and check if the pressure sensors are true or are false, on or off. If they are on, since we are using negated contacts here, this timer won't start. If these pressure sensors for any reasons are false, it means that pressure on those pipes haven't reached the desired value, then these contacts will be true and this timer will start timing. And look, we are using an off delay timer here. Okay, we are using an off delay timer, and so for 15 seconds the down bit will be on. So when the down bit will be on here, so here, since we are using a negated contact, here we'll have discontinuity in the logic of the wrong and the pump will shut off. Retentive timer. A retentive timer accumulates time whenever the device receives power, and it maintains the current time should power be removed from the device. So normal timers, we always need to have that signal logic to be true, otherwise the down bit will go off. But retentive timer doesn't care about the signal or that enable bit. Once it's enabled and it will keep going. However, it will keep going, I mean it will stop the time, but it will keep the down bit or the Q bit true. This is, here we have a mechanical version, and you see that here is a contact, and the contact will be closed once we are in this region. This is a cam and this one is a follower, let's say. So once we are in this region, the contact will be closed. However, if we stop the motor, and that motor should be interpreted as that signal. Once we stop it, the contact will stay closed. Okay, so that down bit will stay closed, plus it will keep the time because the time is based on the position of the cam. So if power is removed from the motor, the shaft stops but doesn't reset. Okay, here we have a PLC retentive timer. Those timers are used when you want to retain accumulated time values through power loss or the change in the wrong state from true to false. And we need to reset them, otherwise the accumulated time won't back to zero. So we need another instruction or coil to reset those retentive timers. Here we have one example. We have push button 1 and push button 2. One is time and the other one is the reset push button. Once we press push button 1, the retentive timer will start. What is the preset time value? Is 9 seconds. If I release that time or this push button 1, the accumulated time will be freezed and the down bit will stay true. So that pilot light will stay still true until again I push that push button 1, and then again it will keep timing. So what if I want to reset the accumulated time? I need to press this reset push button and then the timer will be resetted. Here we have a very nice graph and you could see what's the meaning of a retentive undelayed timer. For the previous example, that push button 1, for example, goes from false to true, and the accumulated time will start to accumulate time. So here at 3 seconds, let's say I release the push button. So you see that the accumulated time will be freeze. But let's see what's going on with the down bits. Down bits will stay off. Why? Because we haven't reached to the 9 second or the preset time value. That pilot light will be off. Why? Because the down bit is off, and this reset input P2 is off because I haven't pressed it yet. Now I press this push button 2 again and the time will start to accumulate, will go up to the 9 second. The down bit now is true, the pilot light is true, and will stay true. So this is the difference between a retentive timer and undelayed timer. Why? In normal undelayed timer, when the input goes off, the down bit or the output bit will go off. But here it will stay true and the pilot light will stay true. And the accumulated time will stay at 9 seconds. But a normal undelayed timer, the accumulated time will be resetted once I release the push button 1. Now I press the push button 2 to reset the accumulated time, to reset the down bit, and the pilot light also will go off here. Here we have one example for retentive undelayed timer alarm program. Here we have one horn, and here we have one key switch to reset the timer, and we have a pressure sensor. So what is the purpose of the retentive on-delay timer? Is to detect whenever a piping system has sustained an accumulated overpressure condition for 60 seconds. So we don't want to hang this horn every time the pressure goes above the preset value. We want to hang this horn when the pressure goes above preset value for 60 seconds, not consequently, but accumulatively. So this is the pressure sensor. Every time that pressure sensor goes on, the retentive on-delay timer will start timing, and when it goes off, it will stop it. For example, let's say it goes on for 5 seconds and goes off after 5 seconds, then the accumulated time will be freezed at 5 seconds. Again, it goes on and off, so this accumulated basically time start climbing up, and when it reaches to the preset value of 60 seconds, the downbeat will be true. Once the downbeat is true, the horn will be on. So the horn will be on until the operator reset the timer. This is another example. This is a bearing lubrication program. Here again we have a switch and we have a reset. We have pump and motor, and we want to lubricate the motor for based on a specific instruction. I'm not going to go through the detail, but I recommend you to read it line by line and do a reverse engineering basically to understand what is purpose of this program. Cascading timers. Program sequential motor starting circuit. So here we have used a cascading timer. It means that we have a timer for one, or the first timer, let's say with the preset time value of 20 seconds, and the second timer will be initiated or started with the downbeat of the first timer. So that's why we call it cascading timer. So the downbeat of the second timer will go on after 40 seconds. 20 plus 20. Annunciator flasher alarm program. So these annunciators, flashers, or basically they are flashers, goes on and off with the specific frequency. In some PLC programming languages, you don't have access to the direct flashing function blocks, so you need to write them by yourself or write the program by yourself. But for educational purposes, to learn about timers and cascading timers, very perfect example. So here we have two timer with both preset time. One second. So you see that we are using negated downbeat of the second timer to enable the first one, and the downbeat of the first timer to enable the second one. And we have three pilot light: green, red, and yellow. The first and second one are basically just simply using downbeat of the first timer. However, on the yes, so yeah, so we are for all of them we are using a downbeat of the first timer. Also, you could use the second timer. It doesn't make that much difference. It's just the one time period shifted forward with the combination of these switches. And you will see that all of these pilot lights will flash. The two timers form an oscillator circuit which generates a time pulse output. Watch this video for the codices implementation, and later you could also implement it in TIA portal by yourself. Cascading of timers for long time delays in some PLCs, I mean hardwares, you have some limitations in terms of using timers with high preset time value, and then you have to go with the cascading timers for longer time delay. So in this case, you see that we are using one timer with 30,000 seconds and the second one with 12,000 seconds for the preset time, and we are enabling the second timer with the downbeat of the first timer, and finally we are using a downbeat of the second timer to control the pilot light, and simply this pilot light will go on after 42,000 seconds when we turn on this switch, of course. Programming for control of traffic lights in one direction. Here we have red, amber, and green lights, and we want to turn these red, amber, and green lights on and off with specific sequence. And there are 30, 25, and 5 seconds time delay between each of these sequence. It's quite straightforward. You see that, for example, here we are using negated downbeat of the last timer to enable the first one, and then we are using a downbeat of other timers to enable the others, and combination of enable and downbeat of timers to control these lights. I'm gonna leave it to you to think deeply about this program and see how it works. Put it on a piece of paper, maybe write a graph and see what would be a time sequences and interval between each lights. And here we have a program for traffic lights in two directions. So we have red, green, amber in one direction, and red, green, amber for the second direction, and of course they should work simultaneously to control traffic of the let's say the conjunction. Okay, so from this slide you are going to create a project that using timers to have the station working as below. This is a programming timer in the distribution station. Initially, when the processor starts, the reset LED should blink with a frequency of 1 Hz. So reset LED, we mean the LED which is located on the reset bottom of the station, but could be any LED. Yeah? So for the purpose of programming the PLC here or writing the program, it doesn't matter what is that LED. 0.5 seconds on and 0.5 seconds off until reset button is pressed. When the reset button is pressed, the start LED should blink for 3 seconds with the same frequency and then turn on and remain on for 20 seconds. Then it should turn off. If the start button is pressed, the whole process starts over. If the system has been on for 1 minute, then it will stop working. Start LED and reset LED will turn off until the stop button or both reset button and stop button are pressed together. So we have start and stop button and reset button, those are switches, and we have start LED and we have reset LED, those are output LEDs. So follow the instruction to learn about TIA portal, how to program and work with the TIA portal, plus how to work with timers. To create the blinking signal, one way is to use timers. You can combine timer blocks in order to do so. Start by adding 2 T on blocks to your code. So see, we have a T on block, drag and drop it to your code. Add 2 contacts and associate them with the output of the timer as shown below. So of course, once you start to create the project, you should choose ladder logic programming for the programming environment, and once you do so, then you could have access to this specific environment, and in the network 1, drag and drop 1 timer. Once you do that, and when you give it a name, you will have 1 instance of a timer in your memory and under your tag tables. Set the PT or preset time of both timers on delay timer blocks to 500 millisecond, which is equal to 0.5 second. How you could do that? You should type T sharp 500 millisecond here. Okay, these are default name for the timers, but you could change the name to whatever you wish. And here, if you start typing the name of the timer, then you could have access to the variables of the first timer, like done bit or Q bit of the first timer. You can simulate your project before loading it to the PLC. Of course, you don't have access to the PLC, but so far you should have learned about PLC sim and simulation if you have watched the related video that I loaded on YouTube as on Moodle. So here we want to use the PLC sim. Click on Start Simulation icon in the toolbar and start the simulation. Okay, so where is that Start Simulation icon? Here. Okay, so you click on it. You will see this window. You need to turn on it. So turn the monitoring on in order to monitor the state of the variables. First, you need to turn on the PLC sim. So when you turn it on, it's equivalent to turning on the real PLC, and you should see this solid green light for the run and stop. It means that the state of the PLC in simulation is perfect. When you load the program, you should see these windows. Okay, so you are loading the software hardware into the PLC sim, and then you click on Start All, and you will do the downloading, and then you could observe the output of the first timer as it should blink. But you need to turn on the state. You should turn on the monitoring of the states, which are those glasses icon. Now we want to have the reset LED blinking until the reset button is pressed. You can add the following rung to your code in order to do so. So here we have the rung, and this is the address of the reset button. Okay, this is the real address of the reset button in the real hardware, but again, you could use any numbers here because you're using PLC sim, but I strongly recommend you to follow the instruction and use exactly the same variables. Simulate your project and observe it while it's running. So if you go online and turn on the monitoring, you should see these basically highlighted lines of green and gray or blue, and you could modify the inputs by right clicking on it. Modify to 0 or modify to 1. It means that, for example, you are pressing the reset button. You can modify the value of tags in the runtime by right clicking on them and choosing modify reset button to 1, and check that the reset LED stops blinking. With the current configuration, when you press reset button, the press LED will stop blinking, but after releasing the reset button, it will start to blink again. Add another network to modify the code as shown below, then simulate it and check it in the runtime mode. So basically what we are doing here, we are using the internal memory for these contacts. So when it starts with M, so when it starts with I, it means that this is a real input device. When it starts with Q, this is a real output device, the reset LED. When it starts with M, this is just one bit in the memory. Okay, so this is a virtual or internal variable that could be used for contacts and coils. So here we are using one internal memory, and we latch that internal memory. Okay, why? Because we want to be independent from the reset button. If the reset button is released, we want to keep that LED going. Now we should control the blinking of start LED. Once the reset button is pressed, modify the code as shown below. The start LED will blink for 3 seconds and then will remain on. So look at how the number of networks are increasing. So we are adding code as we are going forward. And here we have this pulse timer with 3 seconds added to the code. And also here we have this network 5. Read the description here. LED display of the start button on the panel will blink for 3 seconds and then remain on. Now we should control the blinking of start LED. Once the reset button is pressed, modify the code as shown below. The start LED will blink for 3 seconds and then will remain on for another 20 seconds. So we are adding this network 5 and network 6 as we go forward and proceed, and you are basically copying this code try to understand what are the meaning of each contacts and cores, what are the purpose of each. Use the start button to go to the reset mode. Introduce timer. This is the retentive on delay timer, TON-R timer, in order to keep track of the total time in which the system has been turned on. So here we have a network 7 and network 8. Again, be aware of the sequences of the code as we are proceeding, and plus always remember there is no one unique solution, and you could write your own code which will give you the exact same performance. Add a contact associated with the TNOR output on the pass of the start and reset LEDs in order to turn them off. Once the TONR or retentive on delay timer is reset, the LEDs can turn on again. Test your code in the simulation mode, and once you are done, ask the instructor for downloading it on the PLC. So unfortunately you don't have access to the PLC, but again you could download it to the PLC sim and test your code. Testing your code in the PLC sim could be a little bit problematic because you need to modify each variables or contacts one by one, specifically the real input devices, yes, for like switches. For the internal memory or outputs, you don't have to modify it because the program will take care of those variables.